Okay, let's try number 9 in your book. And this is in section 1.7. And the problem states, or it says, the time rate of change of a rabbit population P is proportional to the square root of P. At time t equals 0, here in months, the population numbers 100 rabbits and is increasing at the rate of 20 rabbits per month. How many rabbits will there be 1 year later? So what's our given information, right? We have a given and we have a goal. So what do they give us? The first sentence says the time rate, well, first of all, actually before we write the given information or as part of the given information, we should say P of t is going to represent the rabbit population. Right, it's a word problem, so we probably should write some words. Rabbit population. And this looks like it's going to be an exponential growth model. So the time rate of change, okay, time rate of change, that translates mathematically into dp, where p is p of t, dt. Okay, the time rate of change of a rabbit population is proportional to the square root of p. So if it's proportional, it varies directly, so that's k times the square root of p. So that's the translation. You can also call this p prime of t, or sometimes p prime. But that's the first sentence. At time t equals 0, the population numbers 100 rabbits. So here is, okay, so that's one given information. And it looks like we're given an initial condition, right? At t equals 0, the population numbers 100 and is increasing, okay? Keyword increasing. That means we're gonna take the derivative. So that's going to be p prime of 0 equals 20, because it says it's increasing at the rate of 20 rabbits per month. Okay, so this p prime of 0, this is a rate. Okay, and this is your initial condition. This is what we're starting with, 100 rabbits. And then every month, right, where it's going up by 20 every month. So the goal, right, so we have a given and a goal, and the goal is how many rabbits will there be 1 year later? Well, we're talking about P of t, so we probably want to find P of 12. Why 12? Because there's 12 months in a year. And again, our unit here is months. So this is what we're looking for. So hopefully that wasn't too bad. So again, here is our differential equation right there. And then of course we're going to use these guys. So let's go ahead and try to find P of t. So we have dp dt equals, well, I'm just going to rewrite this. So k times the square root of p. And we need to find k in order to solve this problem. So in order to find our k, let's go ahead and use our initial condition, right, and this rate that they gave us. So we have, again, we can rewrite this as, okay, so equal, so we're going to find k. So the square root of p, okay, well, p is our initial population, so that's going to be 100. Okay, so I substituted this guy right here, and dp dt, well, I mean, our time, right, starts at 0, and so we have p prime of t, but in this case we're interested in p prime of 0. Well, what is p prime of 0? Okay, well, that's 20, so we have 20 equals k times 10, right? The square root of 100 is 10, and if we solve for k, we just get 2. Okay, so our k is 2. So now we can use our k. And then we have dp dt equals k, which is our 2, times the square root of p, or I'm just going to write p to the 1/2, right? Because we're probably going to integrate soon and we want to use the power rule. So this is we have our differential equation, right? We know what k is. So this looks like we can probably separate the variables, right? This is a separable equation. And I'm going to cross multiply. So I have, right, dp equals 2p to the 1/2 dt. And I can probably, right, divide by, so 2p to the 1/2, if you even want to write the dp here, equals dt. And let's write this a little bit nicer. So we have 1/2 p to the negative 1/2 dp equals dt. And we can definitely, we've separated the variables, so we can definitely integrate both sides, of course with respect to p and then t. So this is just a constant. We can take that out, and we get p to the, we're adding 1 over 1/2, which just really means I'm dividing by 2, or multiplying by 2. So we can write it out. We can just do that, right? Instead of dividing by 1/2, it's the same thing. So we have t plus a constant of integration. Okay, so that's gone. So we're left with p to the 1/2 equals t plus c. And if we square both sides, right, we can solve for p because we really want a p of t. So that's t plus c quantity squared. So again, we have a model, right? This really represents p of t, right? It's a function of t. And again, what is our goal? Our goal is to find p of 12. And well, I mean, we can just substitute our 12 for t, but we need to know what our constant c is. So here we're going to use the given information again. And let's see, we have p of t, we can do, let's see, it actually doesn't matter which equation we use. We could, I mean, if we use this guy here, let's see, we get p of 0, right? I was thinking of using this one, but it's the same thing, equals 0, well, that's just 0 plus c, which is c squared. P of 0 is 100. 100 equals c squared, so then c must be 10. Okay, so we found our other c, and so now we have all the information to find our p of 12. So let me just go ahead and write our function, our population function. And so p of 12, whoops, is, well, t is 12, so 12 plus, and then of course our c is 10, and of course that's just 22 squared, and if you multiply that out, we just get 484. So p of 12 is 484. Well, does that answer a question? How many rabbits will there be 1 year later? Well, after 1 year, we're going to have 484 rabbits. So that's it for this problem. Let's see if I can draw a little rabbit. Looks like a car. This is horrible. Let's see. I can't draw a rabbit. There's the tail. Oh, that's horrible. Okay, there's my rabbit.